Alright guys, we're going to start vodcast 10.2. We're still in the solution section, but we're going to start talking about concentrations. This is sort of like the key thing, kind of like moles and stoichiometry and the gas law stuff when we did ideal gas law. Those are sort of key things. This unit here today is of almost equal importance to those things. So what is concentration? Basically, concentration is how much stuff, stuff being the solute, so remember the solute is the stuff that gets dissolved. So it's how much stuff is dissolved in the solvent. And so, like if we looked at these two teacups, this would be a lot, and this would be a little. Now what's the stuff in this case? The stuff is tea from the tea bags dissolving into the water. And we've got a lot more in this one than we do in this one because this one is a lot darker. A lot more stuff has dissolved into that. So that's going to lead us to a couple of important terms here. So obviously, it being science, we're not going to just say there's a lot or there's a little. Those things are going to have specific names. So we have two different ways that we can label these. One of them is concentrated, meaning that there's a lot of stuff in there. And then the other way, which this word might seem a little bit more unfamiliar to you, is called dilute. So in this case, this is a dilute solution because it doesn't have as much stuff dissolved in it. We would say that this is a concentrated solution. It has a lot of stuff dissolved in it. It's not the only way that we're going to talk about it. In fact, that's kind of a, if you remember back to earlier in the year, this is what we would call a qualitative way of describing it. And of course, as scientists, we prefer a lot of times to not do qualitative because I could say this has a lot, this doesn't. What we generally prefer is to have some numbers. So the main way, this is the most common way in chemistry that we're going to use concentration, is something called molarity. If you went into the chemical closet and you pulled out some of the flasks that have labels and stuff on them, I've labeled them, and you might see something that says something like this on it. It might say 1.0 molar HCl. So that would be a 1 molar, capital M is molar, solution of hydrochloric acid. Now, how do we find molarity? It's pronounced molar for a solution, but we're calculating the molarity. So how do we calculate molarity? It is moles per liter, moles of solute over the total liters of the solution. So pretty simple formula. A lot of times you'll see the formula just written like this. Capital M, and that capital is important, is equal to moles per liter. So let's work one. What is the molarity of a solution that contains 24.5 grams of sodium hydroxide dissolved in 500 milliliters of water? So our formula again is molarity is moles per liter. Now here's the problem. I don't have liters or moles. Now liters I can get pretty easy. I can do a real quick conversion there. I can move the decimal 3 places, or you could plug into a good conversion factor like we've been doing most of the year. So there are 1,000 milliliters in a liter, right? Did some of those in gases as well. So that would come out to be 0.5 liters. So we plug that into right there in the equation. But the more complicated part is that we don't have number of moles, right? But we do have grams, and we know what the formula is. So that means I've got 24.5 grams of sodium hydroxide. Now, sodium hydroxide is NaOH. How would you know that? Well, we've done naming and formulas. You should be able to get that. OH is a polyatomic. Crisscross them. They're both +1 charges, and so that's what the formula comes out to be. So we're going to find the molar mass of that. We look all that stuff up on the table. Sodium's 23, oxygen 16, and hydrogen is 1. So that gives us 40 grams in 1 mole is the molar mass. And so we calculate that out, and we get 0.6125 moles of sodium hydroxide. So that then we're going to take and plug in right there. So let's write that out real quick. We've got molarity equals 0.6125 moles over 0.500, really 0 liters. Okay, so we calculate that out, and we're going to get 1.23. And then the units, you could write moles per liter, but more accurately, you should put an uppercase M. It's a 1.23 molar solution of sodium hydroxide. Okay, so relatively straightforward. Let's work another one where you might see things a little bit differently. One of the things that they really like you to be able to do is to explain how this stuff gets made. So that's what we're going to do in this case. Remember, if you recall from the beginning of the year, this is what's called a volumetric flask. It's used to measure volume real accurately. And if you look right here on it, there's a line there. And so that line is an exact measurement. And so we're going to say that we have a 1 liter volumetric flask. Now, why would I make it a 1 liter flask? Because if I look in the problem, I'm making exactly 1 liter of something. Now, this problem works a little bit differently because I have a molarity given to me, but that's okay. We've been working problems for a couple of weeks here where we had different things. So I know my liters, right? And I know my molarity. Okay, so liters, molarity. All right, so I know those two things. So what can we do then to find how would I create the solution? Well, if I already know how much of it I need, how many liters, and I know what molarity I'm looking for, then what I have to do is figure out how many grams of the stuff do I have to weigh out. So how do I do that? Well, I'm going to plug in the numbers that I have into the formula. I have a 1.5 molar solution. It's equal to X number of moles, meaning that I don't know how many moles, that's what I'm trying to find, over 1 liter of solution. Okay, so we're going to do some algebra here. I'm going to multiply both sides by 1 liter. Okay, why do I do that? Because that will cancel them out over here. It'll get X by itself. Okay, so we multiply that out, and that basically is going to tell me that I have 1.5 moles of whatever the solution is. In this case, it's sodium bicarbonate or sodium hydrogen carbonate. Now, again, that doesn't really ask me what I need. It says, how would I create this? Well, I can't weigh out moles in the lab, so I'm going to have to turn that into a molar mass. So how do we do that? 1.5 moles. We're going to find the molar mass. Molar mass of this solution is 84 grams. Okay, again, how do I know that? Periodic table, right? That's how we always find molar mass. 23 plus 1 is 24, plus 12 is 36, plus 48 is going to give us 84. We punch that out, and it says that we need 126 grams of sodium bicarbonate. So, how then would I create the solution? Okay, and this is where you'd sort of write a couple of things out. I'd put 1, weigh out 126 grams, oops, weigh out 126 grams of sodium bicarbonate, put into flask. Now, be a little bit more precise than that, but put into volumetric flask. Okay, and actually, let's correct that into 1 liter volumetric flask. Then step 3 is add water to line. And then step 4 would really be mix it up, but that would be it. So we'd weigh out our sodium bicarbonate, so we'd have some solid down here in the bottom, and then we would start putting water in, and we'd fill up the water until the bottom of the meniscus was exactly on that line, and then we'd pick that flask up and shake it around a few times. Okay? Pretty straightforward. So what that means is that we can calculate molarity, or we could calculate moles if we had to, and we could actually calculate liters. I'm not working one of those problems, but you could. Plug in the two things that you have, solve for the other one, just like we did in the gas law stuff. It's actually easier than the gas law stuff. Now, the way this works a lot of times is that I'm not weighing out a powder or a solid and adding it to a liquid. A lot of times what happens is that I have what's called a stock solution already made up. So this is an example of a stock solution. What we mean by stock is that if I went in the acid cabinet, I already have hydrochloric acid in liquid form there. And it's probably pretty concentrated. So if you look at this bottle, it says hydrochloric acid concentrated. Okay? When we do that, we use something called the dilution equation, because what I'm going to do is I'm going to take that stock solution that's at really high concentration, and I'm going to dilute it down into a more usable form. Now, how does this work? Okay? So we've got 4 variables here. You'll notice that this looks a whole lot like Boyle's law, and it actually works exactly like Boyle's law does as well. Let me move this up because I have a feeling, I'll leave it there and just cut the picture out. I have a feeling you guys might not be able to see that. It works just like Boyle's law. You get 3 things and you solve for the one that you don't know. So here's the way it works. The first one, M1, is the concentration of the stock solution. So like, this doesn't say it on the bottle, but what this probably is a 12 molar solution. Okay, so the concentration of the stock solution is M1. Okay, V1 is how much of the stock solution you want. That's usually what you're trying to calculate. M2 is the concentration that you want to get to, and V2 is how much of the final solution you want. Okay, so let's look at one of these problems. I want to create 500 milliliters of a 1.2 molar solution of hydrochloric acid. The acid in the acid cabinet is a bottle of 12 molar hydrochloric acid. How much of this hydrochloric acid do you need to measure out to make your solution? In other words, what is V1? Okay, that's my unknown. Now, this basically works out just like all of our gas law problems did. You just write out what everything is. The only difference is that standard convention says that 1 is always the stock. So normally in a gas law problem, I would take whatever the first numbers were and make those 1. In a dilution problem, I would look at it and say the stock solution is 1. So V1 is what I'm looking for. How much stock do I need? M1 is the higher concentration always. Okay? Now, that being said, M2, pretty easy to find, 1.2 molar. And then the V2 is 500 milliliters. Now, a lot of you all will probably ask the very astute question of, do I need to turn that into liters to make stuff cancel? As long as you have both concentrations, no, because these two capital M's are going to cancel each other out. And you're just going to get an answer in milliliters, which is what you actually want. That's what you're going to measure in the lab. Very rarely in the lab am I like measuring out liters of concentrated hydrochloric acid. It'd be pretty dangerous. So unless you're working in an industrial chemical plant, that doesn't usually happen. So I'm going to write out our equation real quick. Oh, writing is hard. Okay, so M1V1 equals M2V2. And then we're going to go in and plug in our numbers. Okay, so we know M1 is 12 molar times V1. V1 is what I'm solving for. M2, 1.2 molar. Okay, and that's times 500 milliliters. Now, you could go ahead and multiply the stuff out. Probably wouldn't be a terribly bad idea to go ahead and do that. And if I did, I would get 600 over here, but I don't really have to at this point. You can do that first, or you can do the algebra first. I think this one is pretty straightforward. So I'm going to go ahead and do the algebra first. Again, just like with gas laws, it doesn't really matter what order. Okay, so V1 is now by itself. Molar cancels, and so my units are in milliliters. And then when I actually plug in the calculation, I'm going to get 50 milliliters. So how would I make this solution? I would measure out 50 milliliters into a flask, okay, the concentrated stuff. I'd go in the fume hood, measure it out, and then I would add water until I got up to my final 500 milliliters, and then I would have my 1.2 molar solution. Okay, so now that you got molarity and a pretty good handle on that, let's confuse things just a little bit. The second type of concentration that gets used a lot in chemistry is something called molality. Do not ask me why they would possibly name two things so close together. The difference, obviously, is that there's an L here instead of an R, and that it's a lowercase m instead of an uppercase m. Okay. Now, what's the actual difference in the formula itself? The difference is in the denominator. If you look back real quick, okay, to our formula for molarity, it was liters of solution on the bottom. Moles on the top, liters of solution on the bottom. And if you look at molality, it is moles of solution on the top still, but it's kilograms of solvent, not of the whole solution, just of the solvent. And that's going to change up a lot of things. So let's work one of these real quick. What is the molality of a solution where 15.2 grams of KCl is added to 650 grams of water? So water is obviously the solvent. Water is pretty much always your solvent. And I don't want grams, but the formula for molality is moles over kilograms of solvent. Okay? So that means I'm going to turn that into kilograms. 1, 2, 3, or you could divide by 1,000. Okay, either way would be fine there. So I already know that the bottom here is going to be 0.650 kilograms. But it's the moles on the top. So what do we do to get the moles on the top? We've got grams. The way that we always turn grams into moles is with molar mass. So I've got KCl here. I look on the periodic table and I see that KCl has a molar mass of 64 grams, 1 mole. Okay, and we punch out the math on that. We get 0.201 moles. Okay, so that 0.201 moles then is now going to go, whoops, that's not going to work. That 0.201 moles is going to go up here in our equation. Okay, and we just punch that in our calculator. We get 0.309 m. That is pronounced molal, as opposed to the molar in molarity. Okay, now why would we use this instead of just sticking with molarity? The kilograms thing actually matters a lot because you get solutions that are really dense, and so for water it doesn't really matter. Water, the molarity and the molality are usually going to be pretty similar, but if you've got a lot of solute added in, your molality is going to be very different than your molarity. If you get a really dense solution, then you might need to use the density to figure out the kilogram stuff that's right here. They're a lot alike, and in fact, for most water solutions, they're going to be basically the same, but not always. And we're going to see here when we get to the end of solutions that we talk about colligative properties that we need to use molality in that case instead of the molarity that we would usually use. All right, thanks as always, guys.